Good afternoon. I hope lunch was to your liking. A little bit of a quieter room this afternoon, I think, after the rush from this morning. My name's Richard Wade. I'm an automation architect, according to the slide. I work with the service provider business. I've been working in service providers and with service providers for about 20 years. So I started off working in Europe in the service provider industry in the late 90s, and then came down to Australasia and currently based in Singapore. I run a team of people who specialize in network and systems automation. So that's all they do. They don't sell boxes. They just work with a combination of open source, standards-based stuff, and Cisco products and third-party products to make innovation happen around the automation area. So what I'm going to talk about today is software-defined transport networks. And I know some of the people in the room that I've just had a quick word with will have heard some of these things before, but I know some others in the room haven't. So I'm going to try and keep the information relatively equal. In terms of the area I'm talking about, I'm going to be talking about the IP transport network area. We were asked to put this slide into the deck to show you where we're going to be presenting on. So I'm going to be talking about three main things. I'm going to talk about simplifying IP transport. This is really talking about segment routing. If people have heard about segment routing, I'm going to be talking a little bit about segment routing, and I'll tell you why I'm going to talk about that. I'm also going to talk about current developments in traffic engineering. So how we can manage and manipulate the traffic on our network for performance reasons, reliability reasons, and business reasons, so we can get the right outcomes. And finally, I'm going to talk about automating traffic engineering. So how we can use software-defined networking techniques and platforms and tools to automate the traffic engineering and the segment routing that underlies the infrastructure. I don't think you've seen this slide today. I hope you haven't seen the slide today. Sumit referred to some of these problems earlier on this morning, and especially those of you from larger telcos and service providers will understand the domain breakdown that we have here, where we have the data center domain with its own set of technologies, and this is somewhat simplified as well from a data center domain, with its own operational team, with their own operational tools, their own operational processes, their own planning processes, etc. We have the core network domain, where we have, again, a different set of network protocols, different set of technologies, and again, another operational team that has their own planning processes, operational processes, and tools and systems. And then we have the access domain, which may be part of that same team, but they've got the different considerations in terms of the protocols that are run there. Now, we keep talking about automation. So trying to automate across these domains from the data center through to the edge of the network is really quite complex when we look at this type of model, where we've got different teams with different tools and we've got different technologies that need to be integrated at the point at which these networks join, whether that's data center into the WAN or whether it's the WAN into the metro. And we've acquired these stacks over the past 10, 15, 20 years, and we are where we are today. Where we want to get to, this nirvana that we keep painting this picture of, is where we can have cross-domain automation and assurance, so that we can ideally say, well, I would like a VPN or a connectivity service from point A to point B on my network, and they could be in radically different locations, and I want it to be automatically deployed, and I want it to be confirmed to me that that's been successfully deployed and that adheres to the SLA that I want for that end-to-end service. And we might be talking about having mobile access points hanging off this side of the network for a 5G service, for example, and we might have in the data center some cloud-based service, some data center-based service that the customers want to access. So we want to simplify this network architecture and simplify this network infrastructure so that we can apply this SDN control on an end-to-end basis. And that doesn't mean to say you need to have a master SDN controller that is the one controller to rule them all. You can still have domain controllers, and probably will have domain controllers in each of these specialized domains. If anyone wants to talk about hierarchical SDN and hierarchical service orchestration models, we can certainly grab a coffee and talk about that, but I'm not going to talk about that too much today. The other thing Sumit talked about is how we can simplify the protocol stack by moving towards a single overlay with EVPN technologies, and we can have a simplified underlay using segment routing rather than having separate underlay technologies. And we're all using a common IP transport. I quite like this slide. I mean, those of us who work in the network engineering business know that it's the IETF's business to produce these protocols. It's their raison d'etre. It's what they do. So we end up with services being communicated using BGP and TLDP. We have the transport stack, which involves BGP-LU, RSVPT for traffic engineering. We're distributing labels using MPLS LDP. We're still running the IGP that we were running before, maybe in a more complex manner, and it's still all over IP. So a bunch of operators and IETF guys and Cisco guys and other vendor guys got together and in the IETF created segment routing a few years ago. One of the aims was to really simplify things. And what segment routing does is it simplifies that protocol stack. We get rid of a lot of these intermediate protocols, this label distribution process. We don't need that stuff anymore, and I'll explain why in a moment. And we can get that stack down to EVPN for layer 2 and layer 3 services, running over your IGP with segment routing enabled. If you're using MPLS, then you've got MPLS in here, but you can use segment routing with IPv6, and I'll talk about that on the next slide, all over IP. For my presentation, I'm talking about this bit. I'm not going to talk about the data center bit. The person standing at the back of the room, Abhishek Mandra, is going to talk about this bit in about 40 minutes' time with any luck. So I said I'd give it a little bit of an intro to segment routing. This isn't a segment routing tutorial. I think there probably is a segment routing tutorial taking place in Cisco Live if you want to attend one of those. The main difference between MPLS as you know it today and segment routing over MPLS is that segment routing adopts a source routing approach. Those of you who are a little bit older than some of the really young kids on the block might remember source routing. It has been around before. We didn't think it was a good idea at the time, but now we do think it's a good idea. And segment routing adopts that approach. And the main reason for that is because if you get the source of the traffic to tell the network where that traffic should go, it means you can program from the source to direct it. And from an SDN point of view, that becomes really useful because the application or the source of the traffic understands what SLA it needs, it understands where it needs to go and how it needs to get there. And as we're moving towards 5G with network slicing, and sorry for using the word again, but I will use slicing later on, but I'll actually tell you what it means, is that we can effectively create network slices using this source routing paradigm. And that's what I'm going to talk about a little bit more later on. On the data plane, as I mentioned, segment routing can run over MPLS. So if you're running IPv4, you're running MPLS, you can carry on doing that and you just enable segment routing. You will not need LDP, you will not need RSVPT, you won't need those other protocols anymore. You just turn on the MPLS and you enable the segment routing, and away you go to a certain extent. For the really brave people right now, or the people who want to plan for the future, then you will be able to run segment routing using IPv6. So you won't need MPLS anymore. It'll use extensions to the IPv6 header in order to do that source routing mechanism. For the control plane of segment routing depends on your IGP. It basically uses IGP metrics or extended metrics within your IGP protocols on your network. It uses OSPF or ISIS. It also uses BGP to distribute the information that's required to do segment routing. So that's why you don't need LDP anymore. You're relying on IGP, the existing IGP, to do all that for you. And as I say, we can use OSPF or ISIS. In conjunction with that, we can use an SDN controller, and I'm going to talk about SDN controllers quite a lot in this presentation. For the path options, you can do what you do today. So you can let the packets roam free and let them find their own way to their destination, or you can do explicit paths. So you can still do what you do today with RSVPT and have a very specific series of segment IDs, as we call them, in order to direct the traffic explicitly from node to node, from hop to hop around your network. But if you want to adopt a more modern SDN approach and stop trying to do the really prescriptive control of traffic, you can use dynamic paths. So how are those dynamic paths calculated? Well, I said it uses the IGP. So you've got two options. If you've got a pretty simple network, or it's a small greenfield area that's only a single IGP domain, so it's not multiple ISIS areas, it's not multiple OSPF areas, it's a single domain, you can do it just using the head end, because from a Cisco point of view, all of our path computation for segment routing is part of iOS XR. You don't need anything additional to do the path computation. So you can do dynamic paths using just iOS XR. If you've got a slightly more complicated requirement, so you want to do complex disjoint paths, or you want to do multi-domain stuff, that's when you need to introduce a centralized path computation element, or SDN controller. So this diagram shows how the path computation element fits into the picture. The path computation element, and in Cisco's terminology, we call it our segment routing path computation element, which is a really simple and obvious name to call it, I think. It collects information from the network using BGP-LS. So I said BGP was used in this. This is one of the uses for BGP. We use BGP link state, and what happens with BGP link state is we redistribute our IGP into BGP, and we have a BGP link state session from points in the network to the path computation element. What that means the PCE gets is it gets to understand the topology, and it understands the metrics and all of that information that was inside the IGP. So where we've got the IGP that has metrics for things like delay or things like path cost or link cost, that is redistributed into BGP-LS and is learned by the path computation element. The path computation element can then be asked questions by nodes in the network using PSEP. And the node in the network can say, I would like a path from point A to point B. Please, can you compute a path given these objectives? And that might be to minimize the IGP metric. It could be to minimize the delay, for example, and we'll talk about that in a moment. The PCE can learn that topology from multiple domains. That can be a separate BGP domain, or it could be separate IGP domains. It can then form a single topology model for those multiple domains, which means that you use the PCE to do an end-to-end path computation across these multiple domains. If you were using a single node in the network, obviously that single node doesn't have visibility of the other domains, which is why we can't do that using the distributed model. We need to have a centralized model in order to do that, because it needs to peer with all the multiple domains. So I was talking about the segment list, this segment ID list. So in this example, when we ask the path computation element for a path from node 12 to node 7, it asks the PCE for a path. The PCE calculates a path and returns it, and it returns a list of numbers. In this session, I'm not going to go into what those numbers are and why they're called what they're called, because we haven't got the time to do that. But what you can see here, and the one thing I wanted to call out, is that from node number 12 to node number 1, we've actually got two paths. And that is denoted by the segment ID 16001, which is directing the next hop in the segment list to this node here. Now, the reason we've got two paths is that there are some equal cost paths to that destination. And I said we use the IGP, and this is something you get for free with segment routing. You don't need to say share paths to get to that destination. It'll use the IGP equal cost multipath in order to get there. So that's one of the advantages of segment routing. Okay, so the PCE, the head end will ask the PCE for the path, the PCE computes the path, and the PCE returns the segment ID list.
Just a question.
Sure.
So what if there are PCE files?
What are the PCE fails? You can have multiple PCEs, and you can have multiple PSEP sessions with multiple PCEs. You can synchronize tables between PCEs, or you can run them completely independently, and it'll just reestablish a session and just do a path computation. The PCEs will be learning the topology from the network, so they'll be up to date with that. The reason you might want to synchronize some information is that when you do what's called delegating a path to a PCE, that PCE maintains state for that path. So you might want to synchronize that with your backup PCE. Yeah, you can synchronize that state. Yeah, absolutely. But everything else they'll be learning from the network in real time. Yeah. Treat your PC a bit like a route reflector. They're the same sort of configuration, same sort of redundancy model as something like a route reflector.
But that's sort of
Yes, yes, yes. The PC is essentially just an iOS XR instance, and you can run it on a router, or you can run it on a virtual instance as well. Yeah. So what we want, the model I just gave you here, you know, if we're returning a list of segment IDs in quite an explicit manner from here to here, and we're configuring those at the head end, this is starting to look a little bit like what we do today with RSVP-TE a little bit. We're still in that domain of wanting to be very precise and controlling of our traffic. Where the current developments in traffic engineering are is actually moving away from this explicit configuration. What we want to try and do is remove as much state from the network as possible. We don't want to configure the core network with explicit paths. We don't want a mesh of RSVP-TE tunnels. We don't want to have explicit paths configured in iOS XR config at the head end. What we want to do is move towards a policy-based model that gives us essentially intent-based networking, which is a little bit of a marketing term, but I'll show you what that means in a moment. If we can define a policy that says, in order to get to this destination, ask a path computation element for the best path, which will minimize delay, if you've got very delay-sensitive traffic. Or minimize a certain metric if you've got certain paths that are cheaper, financially speaking, than other paths. So you can start to engineer your traffic using policies rather than explicit segment lists or paths that you've described in the network. And what we want to be able to do is to instantiate these policies only when required. And I will show you how to do that right now. So this slide is a bit of a building slide, but what it includes is a segment routing policy that has been configured on this node 6 here at the edge of the network. And this segment routing policy, as you'll see, is to minimize delay to the destination of point number 4. In this example, what we're going to describe is how we can use segment routing policy to be instantiated on demand in order to reach an IP subnet which is beyond node 4. So that's quite complicated. We've got a network over here which is beyond node number 4, and we want to get there from node number 6 using a minimal delay. So what we can do is we can advertise that subnet, that destination, from node 4 via the route reflector, and node number 6 will learn that that route, that destination, has appeared in the RIB. We can also color that route. So using the BGP community, we can give that route a number. It could be number 10, doesn't really matter. Whatever you determine purple to be in this instance. But the intent of that destination with that color is that we want to minimize the delay metric. So when we're doing a path computation process, we're going to say, find me the lowest delay to that destination. And that's what the PC is going to have to answer. So when this head end sees that route appear, it instantiates the policy. And that policy says, ask the PCE for the shortest delay path to that destination to get to that subnet. So this guy has asked the PCE. The PCE already knows the topology. It already knows all the metrics, as we just described. So it can calculate a path to that destination. So it executes we call it an ODN, an on-demand next hop template. And I'm very sorry, it's a bit of terminology. Feel free to catch me in a coffee break to go through ODN templates and policies and all that stuff in more detail. All it means, though, is that it's going to instantiate that policy to request that minimum delay path. It then gets a label stack from the PCE that says this is the route that you should take to get to that destination. So nothing's been configured in this number 6. We haven't configured any explicit paths. It's purely getting it from a policy which was an intent and a path computation element. So this is, from a network engineering point of view and a config point of view, this is super simple stuff. The next thing that we can do is we can automatically steer traffic into that. So the one thing I forgot to mention on the previous slide was that when we create this policy and it's been instantiated and we've got this path, we actually get something called a binding SID from a segment routing point of view. And a binding SID just means a segment ID, a segment routing ID, which represents this policy instance. So if we have a packet coming in that has that binding SID, it's automatically going to get switched onto that policy. And that's what this slide describes. So the intent-based automated steering is when we get traffic coming into node number 6, if the outer label of that MPLS packet is this destination, which is the purple path for that destination, it'll automatically go onto the low delay link, the low delay path. Sorry, it is a little bit complicated. What we're doing is we're automating how traffic gets onto a low delay path by pushing a specific MPLS label onto the top of the packet. That's it.
And is it possible with different domains, like if one other domain is LDP, RSVPT based domain?
We can stitch RSVPT into segment routing domains. I'm going to say yes, but I'd need a deeper discussion with you about how exactly we would do that. Yeah. So by default, when you've created a policy, traffic will be automatically steered onto the path for that policy. You can turn that off. But this does mean if you leave it on, it means you don't need any policy routing, you need no ACL stuff at the edge of your network. There's none of that configuration to do. There's no policy maps, nothing. It just goes straight into the segment routing policy that's been created. So I said I was going to talk about slicing. So we can build on this to create network slices. So where we've got a destination on the network, we know that we're going to get a binding SID for this, as I just described what a binding SID is. A binding SID is a destination for a given policy. And that policy could be one that says minimize delay. It could be one that says minimize TE metric or IGP metric. It could be a number of different things. So what flexible algorithms allow us to do is something that's really useful when we're doing that dynamic path computation with the PCE. We can essentially partition our network into different nodes that can perform different types of, that are allowed to be part of different types of path computation. So just to be clear, or try to be clear, you could slice part of your network to be a low delay slice and say these nodes, let's say across the bottom here, 6, 8, 7, 4, etc., they are part of the low delay slice. So all my low delay traffic, when I do a path computation, it's only going to use those nodes to make the computation. So it could be any of these nodes. In this case, I've blocked off this one here and said, no, that's out of service. It might be under maintenance or something. So it can only use these here. But this is the low delay path. It didn't go to number 3 because that was a higher delay for some reason. It could be a metric-based path. So we could choose to create another slice that only uses IGP metrics. So this next slide talks about this in a bit more detail. And this is the last of the slicing and complex segment routing stuff. It doesn't get any more complex than this today. What we can do is between node 0 and node 9, we can have multiple ways of reaching those destinations. And we can reach them based on delay, or we can reach them based on IGP metric. And depending on the binding SID, and I mentioned that before, if we use 16009, that would be algorithm 0. Algorithm 0 is just IGP metric, but it includes all of the nodes. This segment ID minimizes IGP metric, but it's only the green nodes that can be used to calculate that path. We can use 16909, which is a delay-based metric, and that's only the red nodes. So that means that we've got many different options to reach the same destination depending on what our intent is. And that's what I want to keep coming back to. It's what you as a network engineer, as a network architect, or as a business owner, how you want to slice and dice your network infrastructure. So you could have lowest common denominator of the one on the left, which says, just give me the shortest path, because it is an SPF calculation that we do here. It just depends on what metric we're using. So you can do an SPF calculation across all the nodes. So you can end up with lots of different equal cost multipath routes to get to your destination. You could say, well, actually, this is a certain type of bulk traffic, but I only want it traversing these nodes because that's my cheap path, actually. So I'm going to partition that off onto the green slice. So that might be your super cheap transport slice for the low-cost customers. But then you might have a low delay slice down here for your high priority and high value traffic that needs low delay. And when you ask the path computation element, give me a path, it will rule out all of the other nodes and only do the path computation based on the ones that are marked as participating in that network slice. So I know lots of people talk about network slicing, but one of the reasons I wanted to show these slides is to show that we do actually know what it means and we can actually implement it. And these features are available today in iOS XR. So we can run this, and I've got a lab that can demo it. So if anyone wants a demo of this stuff, we can show it.
And is that like just a command like flex algo, and then it just automatically?
Yeah, it's not super complicated. In fact, if you go to segmentrouting.net, there is a tutorial on flex algo, and it shows you the configuration and all that stuff there. Yeah, there's a YouTube video as well that shows how it works as well. So for some people in the room, this is okay, they've got it. For other people in the room, this might be really, really confusing. But I think we'll all agree that you might not necessarily want to be laying your fingers on this config all day, every day. So I'm going to talk about how we can automate it and hide all this stuff under a layer of abstraction. Yeah. So some of you may have seen this type of diagram before. I'm not using product names in this particular diagram because it doesn't really matter. It's the concepts that are important. So where you've got the top layer, the service orchestration, if you remember the first slide that I showed, it was about this nirvana of having this multi-domain, multi-layer service orchestration where we can have systems or people northbound of this service orchestrator making requests via a web UI or an application or a portal or something or another OSS tool that will basically take care of all this stuff underneath. So the service orchestrator can talk down to the network using something like netconf and yang if you're familiar with those technologies. If your infrastructure doesn't support netconf and yang, then we've got CLI interfaces to multiple different vendors. Is there a question?
Yeah, sorry, is the delay computation or this is automated, right? You've got bandwidth path computation, topology path computation. What about delay?
Delay, right, interesting one. Okay, let me go back to this complex slide. So what we can do is we can actually use MPLS performance measurement to do active probing. So every few seconds there's an active probe that goes between the routers, and that is actually redistributed into the IGP and reported up using BGPLS to the PCE. So it is actually you can do configured delay if you want to use configured delay, or you can, in the latest releases, you can use MPLS performance management to get the result. Yeah. So we don't need to do that on this. So we're not using an OSS tool to do the performance measurement. We're actually using the network itself. So the different layers in this. So at the top layer, we've got service orchestration, which will present a nice abstraction of, I would like a VPN from point A to point Z, just enter the numbers and I'll do all the rest. So that hides all the stuff underneath. Underneath that, we need to do a few different things, as we talked about. We've got topology path computation, which is the PCE that I was talking about. But when it comes to things that need a more complex model, like how much bandwidth have I got from point A to point B? Have I got 1 gigabit per second available between Adelaide and Melbourne or something like that? That's when you need to ask the bandwidth element. Everything else can be taken care of by the topology element. Could I just get a time check? How long have I got?
You've got plenty of time.
I'm okay? All right.
30 minutes.
30? No. I think it's 15, mate. Okay. Okay, so I'll go on to the next slide. So the first thing I'm going to talk about is service orchestration. Some of you may have encountered Cisco talking about Cisco Network Services Orchestrator, Cisco Nso, which was an acquisition that Cisco made a few years ago from a company called TLF. TLF and its technical staff were very involved in the IETF creation of the netconf and yang standards, which are open standards, they're RC standards now. Cisco acquired the company because of the innovation and their knowledge of Yang and netconf, and also some of the technologies that are inherent within the Network Services Orchestrator package and tool. For those who aren't aware of it, I'll give a very brief introduction. Cisco NSO is really good at separating your services from your infrastructure. It uses a modeling language called YANG, which stands for Yet Another Next Generation, which is a wonderful IETF pun. We model services and we can model devices. Now, the reason this is important is that if you've created a layer 3 VPN or a layer 2 VPN or EVPN, whatever service model, you don't want to have to mess around with that model every time you change your infrastructure. If you want to swap vendor A for vendor B, or if you want to upgrade your software to a new release, you don't want to have to start messing around with your service models. It shouldn't affect what you do in your L3 VPN. Your L3 VPN doesn't care what routers and switches you've got underneath. So we have a service model that can represent things like services, and then we have device models that represent all the infrastructure. As I mentioned before, we can use native netconf and YANG to talk down to the devices, which is awesome because then it becomes essentially plug and play. Because netconf as a management protocol can say to a device, tell me all of your YANG models, what can you do? And the device will send back basically the YANG models, and then NSO knows exactly what that device is capable of. So that's a really good thing about netconf and YANG. But if you don't have netconf and YANG, we have something called network element drivers, which you might know as plugins or modules or whatever your other software vendors call them. Essentially, they're southbound interfaces, southbound adapters to the infrastructure. Now, that could be SNMP, it could be TL1, it could be CLI Cisco, it could be CLI another vendor or another vendor, it doesn't really matter. We've got NEDs for many different devices and vendors. So when NSO receives API calls using REST or netconf or through the SDKs for Java and Python, etc., or from the web UI or CLI from an engineer into a service model to provision a service, the good thing with NSO is that it can translate that into device instructions using its device manager and something called a fast map process, and communicate southbound into any vendor, any device, any domain, whether it's optical or IP or data center or firewalls or VNFs or whatever you want. So that's why NSO is really good, and that's why we like it. In this instance, what I'm talking about with segment routing, transport and traffic engineering, is that the service models here would be things like an L3 VPN or an EVPN. It would be modeling those SR transport services and giving you an API or an interface to those TE overlays that you're creating. And you can expose those VPN service models northbound via APIs for integration into your workflow processes or your web portals or something like that. On the device model side, it's going to configure the infrastructure using a CLI or netconf, and it's going to configure the IGP, the BGP, the segment routing. It'll configure those head-end policies. So NSO would take care of pushing those policies into your head-end routers. There is another way of distributing those if people want to talk about it using, you can do it using netconf or BGP or some other method if you wanted to. And it can also configure the PCE, so it can bring up the path computation elements, that sort of thing. So that's what NSO would be doing in these use cases that I'm talking about here. The next thing I'll talk about is the bandwidth path computation. So what's required and why is this required? For this role, we've got WAN automation engine, which is Cisco Way, that some of you may have encountered. Way's got two roles. It can do a planning role, which is essentially offline planning. So if you're in the planning department, Way can gather information from your network. It can understand what it calls traffic demands, which are the flows of traffic across your network. And then it can create a very rich model of that traffic. So it models your network infrastructure, it models your service overlays, it models your traffic demands. So when you're asking it questions like, what happens if this link fails? What happens to my traffic flows? Well, Way can do that, and using the graphical user interface, it can show you a heat map, basically, of if that fails, this link is going to be overloaded, for example, because it understands what the IGP is, it understands your traffic flows. So it can do the offline stuff, and it can do predictive modeling. We can also look back over time and see historical and also project into the future as to what things might be. The other use, which is what I'm talking about here today, is the automation use case. So we can use Wave for these bandwidth questions. Because it's already got that topology model and that traffic model, we can say to Wave via the APIs, if I want 1 gig from point A to point B, what path should that take? Or can I even get that if I want that much bandwidth? So this is where Way integrates with the SRPCE, the segment routing topology model, to give it that bandwidth knowledge. If you don't want to ask those questions, if you don't want to ask about bandwidth use cases, you don't need Way. Okay? This isn't a mandatory component. You can just use topology stuff if you want to just do topology stuff. No, these are so they're separate software elements, and they can be. And I'll show you on the next slide. Actually, you can deploy just NSO, you can deploy just Way for planning purposes, and you can deploy just the topology component. So it's a mix and match thing, but they all go together and they're all integrated, and they can operate as one stack. Yeah. The APIs between these devices are all open APIs. They're all REST APIs or Java APIs, Python APIs, etc. NetConf as well. So I mentioned the segment routing path computation element, and that's where SRPC comes in. So this is just a simple block diagram because actually it's quite a simple platform. There's not a lot to describe. It learns about the topology and the IGP information using BGP-LS. So it forms a multi-domain topology model. As I said, it can do different BGP domains, different IGP domains, etc. It then has a path computation element, and that path computation element is exactly the same algorithms that are available in iOS XR on your head end. And this goes back to what I was saying earlier. You don't need a separate PCE if you haven't got multiple domains. You can run it all on your head end because it's in iOS XR. So we've got the same algorithms, the same processes run on this as run in iOS XR. So you're not losing out by not having the PC, the topology PC from that point of view. The deployment can be BGP or PCEP, but it's got northbound APIs. We've got REST, RESTconf, and NetConf APIs. I have got another presentation where I go off into a Jupyter notebook and start pinging the APIs to show you what you can get out of it. But you can get a lot of really useful information out of these APIs if you're in network ops. So with a simple REST call, you can get a plain text or a JSON dump of your entire topology with all the metrics. So you can discover your entire topology, how it's connected, each interface and sub-interface and all the metrics from a simple API call to this PCE because this box has learned about it. So if you want a one-stop shop for that information, this is a really, really good idea. So this is probably the most crucial one for segment routing traffic engineering. If you want the bandwidth use cases, you need Way on top of this. If all you want to do is topology-based stuff and metric-based stuff, this is absolutely fine. And this is basically an instance of iOS XR, so that gives you an indication as to the pricing for it. So where we've got to is we've got this architecture of all this stuff, and you just asked the question about, do I need all this stuff? Well, good question, because doing it all in one go is a lot to digest. There's a lot of technologies I've talked about. There's a lot of platforms here from an automation point of view. So I thought I'd throw up, this is the last thing I'm going to talk about, an example of what some of our customers are doing and what journey they're taking to get to this nirvana of automation. Where a lot of people are starting right now is building this foundation for automation. A lot of it's about trying to automate the provisioning process, solving the problem of having multiple different vendors, multiple different operating system types, multiple different ages of equipment, trying to get over this hurdle of some of it's programmable and some of it will never be programmable. In fact, it'll rust before it becomes programmable. NSO as an orchestrator, or any domain orchestrator with these technologies, can do that. And it's probably a good starting point because it means you can hide all the complexity and legacy under an abstraction layer, and then at least you're programming and interacting with a single abstraction layer. It does multi-vendor provisioning, multi-domain provisioning. So this is where a lot of the customers are starting with. Once they've got that provisioning capability and that abstraction layer, they're adding on the optimization and automation stuff. And that might be your path computation element. So phase number 2 might actually be coupled with a move to segment routing. So they might choose phase 2 to move from RSVPTE to segment routing as a next stage of their network evolution. or it might be a greenfield build, so they're building a new area of network. So in this phase 2, you can introduce path computation, you can introduce segment routing, you can look at segment routing traffic engineering. Excuse me, you might introduce the path computation for bandwidth as well if you wanted to do that. For phase number 3, which as you can see here is a couple of years out, so this takes time, and we all work in this industry. We know we're often very ambitious with the timelines when it comes to deploying this stuff, but being realistic, this is a multi-year journey. So a couple of years out, you're starting to look at maybe closed loop automation. If you're a bit less brave, you might want to do open loop automation, and open loop automation is basically where you're using all this data and analysis and predictive capability and maybe even machine learning and analytics tasks to make a recommendation to a network operator. And the network operator looks at it and says yes or no, or actually push that onto a queue for more evaluation. So open loop is actually also a model that some of our customers are taking before they go to closed loop. Closed loop stuff, for example, might be BNG IP pool management. So if you're running farms of BNGs, you might want to gather information from those BNGs via streaming telemetry about how much IP pool space they've got left. When it falls below a threshold, automatically provision new IP pools to your BNGs. And the reverse, when you've got an excess of IP pool allocation to a certain BNG, automatically recoup pools from those BNGs, just to optimize your IP pool usage across your BNG farms. So that's one example of closed loop automation that we can do today. The next and final stage is where we reach this sort of end-to-end network slicing nirvana, where we've got the transport network, automated SDN control, path computation, all the toys. We've got the data center with SDN control overlay and abstraction, and we want to look at stitching these things together, even into the virtualized network domain, so for VNF instantiation. And that's where we want to reach this nirvana of the end-to-end automation and interconnecting that data center domain with the WAN domain. And that leads me into the next presentation, which I'm not going to give, Abhishek's going to give, which is about SDN in the data center domain. So I've talked about this bit, Abhishek's now going to talk about this bit and how we can connect the two together. Any questions? I'll be around in coffee and all that, so unless you want to do anything now. It's for short on time. Don't sit down. Thank you.
Any questions? Any questions for Richard now? Questions? No questions?
I think might be one of you.
Cool. Yep. Please.
Just a comment. I think it's this phasing approach is necessary by everyone, just to have a bit of a play, actually, just to understand the automation process. So I know that we're certainly looking at the auto provisioning, how to make it easier to integrate a site or allocate IP addresses, get away from the manual process of allocating IP addresses, do that automatically, and we're probably going straight to phase 3, even with I guess looking at analytics and how to use that as a feedback loop into other things. So that's a bit smarter, and rather than reactive, be preemptive with our systems. Yeah,
I think we do find that some customers they're okay automating things like the IP pool management, like you say, but when it comes to automating and doing closed loop around network traffic engineering, everyone gets a much more nervous, understandably more nervous approach, because they're manipulating the live traffic flows, whereas there are certain functions that people are more comfortable with fully automating.